Binomial probability. Binomial is a word that we usually associate not with probability, but with polynomials, right? And that's why we were looking at expansions earlier in the year. But as it turns out, and you can almost kind of anticipate that, you know, when we're doing probability and arrangements, often what we're doing is we're stringing things together, multiplying things together, and that's kind of the same building block as polynomials. So maybe it shouldn't be that surprising that they actually come together in this unusual way, okay? So we're going to look at how to tackle questions, probability questions that require this specific technique, and it is a very specific technique. You can almost always tackle a probability question that you can use this on in other ways. There are almost certainly other ways, but where it's relevant, these are the fastest, okay? Now here's the thing. These questions, they don't come up with a big flashing light saying this is a binomial probability question. You yourself have to know when binomial probability is appropriate, and there are two things you need to look for, two qualities, okay? Or maybe three. Firstly, we're looking at multi-stage events. That's kind of a given. Like in extension 1, all of the interesting stuff is multi-stage, okay? We want this and this and this together, okay? So the first thing, multi-stage. Secondly, all the stages, they have to be identical. They have to be identical. I'll let you have a think about why, as we progress through this example I'm going to give you, why the stages have to be identical, otherwise this thing, this part of it, breaks down, okay? Last stage, and this is implied by the name, for each stage, not only are they all the same, but they all have to have only 2 outcomes. Only 2 possible outcomes for each stage. Okay? Now, as you'll see in a second, even though many situations inherently have multiple outcomes, like say throwing a die, okay, depending on the situation you get given, depending on the probability you get asked for, you remember what we said before about a problem well phrased is half solved. Well, you can often phrase it in terms of only 2 outcomes. Okay, so let's do an example. And I'll go with the die, rolling a die. And suppose what we want to do is we just want to work out how many 5s we can get. 5s, okay? That's all we're interested in, okay? So even though a die is a 6 outcome situation, right? I'm just thinking it in terms of 2 outcomes, namely 5s or not 5s, okay? 5s or not 5s. So here's our probability tree. I've drawn it out with 3 levels, okay? 3 is pretty much as you're expected to do in an exam, really. As you start to go further, it starts to become a bit impractical just to draw the diagram. But as you will see, one of the strengths of this technique is that you can use it without a diagram, if you understand what's going on. So very quickly, just to start off with, let's just create the diagram, because I'm going to refer to a few things here. So I'm going to start with 5s, right? There's one alternative, and not 5s, okay? So just like flipping a coin, I suppose. I'll fill it out and you can do the same. Now let's consider this. I'm not going to give us any particular questions. We can sort of build our own questions out of a situation like this, okay? For instance, a classic kind of thing to ask would be, what's the probability? Too many markers. What's the probability of all 5s? That would be a pretty straightforward question to ask here, right? Now, we don't need anything in our previous permutations and combinations kind of knowledge to solve this particular question, right? All 5s, how many of these in my sample space of 8, how many of these options are the ones I'm interested in? Which ones are the favorable ones? Just this one at the top, right? That's the only one I'm interested in. And of course, you just use the product rule to work out what the probability will be, right? Now, this is the important thing, right? You got 2 outcomes, but they're not equal. Obviously, they're not equal, right? What are the probabilities on these branches going to be? A 6th, right? Okay, and of course you can fill in all of the 5/6s that go along with that, but it gets a bit tiresome pretty quickly, okay? So I'm only going to put on the stuff that I need. So therefore, this probability is easy. This is just 1/6 cubed. No problems, which of course is not especially likely. 1 in 216, okay? But let's think about other different options here, okay? For instance, that was the probability of getting all 5s, right? The probability of getting no 5s, is going to be a different probability, obviously, but it's just as easy to work out. Okay, so I'm just going to skip that for a second. Right? What about, well, what would you like to pose to this kind of situation? What would be a natural other question that you might get asked? What's the probability? Say that again, Smith.
At least 1/5.
At least 1/5. Okay, we'll get to at least 1/5 in a second. Let's just take a simpler case, which is 1/5. Okay, 1/5, because that's got a couple of cases, 2 or 3 cases in it. Okay. If I say the probability of 1/5, exactly 1/5. Okay. Now in this case, because I've picked out, you know, only a number of branches where it's quite easy to count, you can literally see it. You don't have to do any fancy sort of stuff to work out how many of these options will fit that, right? Which are they? Which are they? 1/5. I can see a 5 here. Yeah. I can see 1/5 here and then here. So there's 3. You can count that up fairly easily, right? But like I said, if I expanded this out, if I just went one more time, you don't have 8 total choices, so you've got 16. And then if I go another time, you're 32. You can't draw the diagram. You can't count reliably in a time-efficient way. Surely we can work out a better way of working out, or why is it 3? Is it just 3 randomly? It's not 3 randomly, right? Why is it 3? Where does the 3 come from? Now, to get an answer to that question, think about this. Think about this question that we posed, okay? There's 1/5. Do we mind when the 5 is rolled? Do we mind? We don't care, right? You could roll it first or in the middle, or you could roll it last, okay? So therefore, in terms of our arrangements language, is this talking about permutations or is it talking about combinations? Are you sure? Good. You are sure. Not because I tell you. Yes, of course it's combinations. Because I don't care about order. These are all the same. That's all I'm interested in, right? So therefore, this is not just 3. It's not just that there are 3 ways to get this. It's that there are 3 choose 1 ways to get this, right? Look, you've got 3 different things to choose from, 3 5s to choose from, but I only want one of them. I don't care where he goes. I don't care where he goes, right? That's why it's 3C1, not 3P1. Does that make sense? In fact, in this whole situation, I don't really care about order at all. I just want, well, I want one of them somewhere, okay? So order's not important to me. Right, now, there are 3C1 ways to get 1/5, okay? Well, let's have a look at one of them. Let's have a look at, say, this one. Using the product rule just like we did before, what's the probability of just this event? Just this event. Well, if I follow the chains through, I started here, then this one's going to be 5/6, and then this one is going to be 5/6. Right? So the probability of just this instance is a 6 times 5/6 times 5/6. No problem. Okay. And when you have a look at the next instance, I mean, we can work this out, but we don't need to, do we? Right? Because, like I said, I just want this. I don't care about the order, right? And every branch is identical, right? Every set of events. So all I need to do is just take these same numbers and rearrange them. That's how I'll get this, right? I'm going to get the not 5 first, and then I'll get the 5, and then I'll get the not 5 again, right? And of course, you don't need to fill out this last one. They're all going to be the same, okay? So therefore, what I've got here to put them all together is I've got 3 choose 1 ways to get 1/5. And then when I think about the probability of each of those ways, it's going to be, well, you've got to get a 5, and that's the probability of a 5. And you've got to get 2 of them being not 5s. Does that make sense? So let me sort of put this out in colors. Right? This is the number of ways, right? This is the probability of just getting a single 5. Okay? And these are the probabilities of getting a not 5, and I want 2 not 5s because I only have 1 5. Sorry, too many numbers. You following so far? Is that all right? Okay, now, without going ahead and drawing it onto the diagram, you can probably anticipate what's going to happen if I say, well, what if I want 2 5s? How would you build this taking this pattern here instead of going to the diagram, which in this situation is just barely doable, but as we expand out the number of stages, starts to become not worth it, right? I've got 3 components, three components, right? First, I want to work out, well, how many ways is this possible, right? How many arrangements are valuable here, are favorable? And the answer is 3, choose 2, because I want 2 5s, right? Now, what will be the probability of all of these different ways added up together? Well, probability of a 5 is a 6th, and I'm going to get 2 of those. In what order? Doesn't matter, okay? I'm just going to get 2 of them, yeah? And then, of course, you're going to have one of the numbers not being a 5, so that's the probability there. Okay? So, in fact, this is the same thing, just for a different scenario. Okay? So, have a think about that. Now, if you put together, I've got one case here, one case here, one case here. There's one case left, right? And that was the one we said right at the beginning, which is that they could be no 5s. No 5s? I didn't do it in a very good order, did I? Okay? But we can build this up, right? I'm going to do it the same way. 3, choose how many? 0. I don't want any. Alternatively, I suppose you could say it's going to be 3, choose 3, right? Because I'm choosing 3, not 5s. We've got symmetry here. Doesn't matter. They're the same. Okay. How many lots of a 6th am I going to get? None of them, because this is the probability of 5, and I don't have any, right? And then, of course, I've got 3 of the not 5s, and we already know what that probability is going to be. Okay, so now you can actually see that this, even though it's correct, right, it's missing bits. It's missing the fact that actually, how many ways are there to get all 5s? And the answer is there's one way, 3, choose 3, right? And then of course there's all of the not 5s here, but there are none of them, so that's why they don't factor in. This is one and this is one, which is why we could get away with not writing them, okay? Now this is all the cases, right? This is the whole expansion. So if I add all of these up, what would you expect to get? This is all the total events, right? Everything. So if I said, what's the probability of any of these happening? Well, one of them has to happen, right? So the probability will be 1, okay? But you can see, if you add these up, this is where this comes in, right? If you add up all these together, what is this? This is the expansion of something. What's it the expansion of? We said this is equal to 1, right? Okay, because you add them all up, from a probability point of view, they all have to add up to 1. But what it is, well, you know, here's your A and here's your B, right? A 6th plus 5 6ths. And then these powers here, this one, this one, this one, this one, they all add up to 3. Of course they add up to 3, right? So when you expand this out, you've got one of the first one, then 3, and then 3, and then 1, just like you would expect from Pascal's triangle, okay? But of course, you know, you could just add them up and cube it and you get 1. Duh, right? So there you go. The polynomial comes in when you consider all of the cases together. Does that make sense?